You can use a tree diagram to do pretty much every probability question. Not everyone, but almost everyone. Let me give you an example of how you could use a tree diagram. Here's the event, and two things can happen. Those are called, this whole thing is called an event. And if I flip a coin, you're either going to get heads or you're going to get tails. Then you can write the probability of that right here. 0.5, 0.5. And now, if you want to figure out the probability of a heads, you just follow that little branch and it's just H. And your answer to it is, well, 0.5. So your probability of getting heads is a 0.5. So what if it's more complicated, like I'm flipping a coin and then I'm rolling a die? Well, just one die. We're going to start with that because if I roll 2 dice, do you remember that there was 36 combos that could happen? So I'm just going to roll 1 die. So I flip a coin and I roll a die, and I'm not telling you what I just got. I would like you to predict, and you'll see probability in action here. What did I just get? And some of you will be right. I flipped a coin. Don't say it out loud. I want you to take your best guess on did I get a heads or tails, and did I get a 1, 2, 3, 4, 5, or 6? Just guess. Write it down. And what we'll do is figure out how many people got it right. In a moment, I'm going to ask you to show the guess to somebody else. Why? Because I hate it when kids are like, that's what I said, and then we have no proof. Like, there'll be some kids that guess this right. All right, so show the person next to you what your guess was. What? There's heads or tails, and then a number. 1 through 6. Okay. Anybody that guessed 7, sad, but it's impossible. It's really common for people to think there's a 7 on the die. The biggest number it goes to is 6. So it was, well, first of all, I'm going to say heads. Now, how many of you are out already? Do you get that's about half the class? Does that make sense? All right. It's heads and then a 6. Who had it? Raise your hand if you did. Nobody picked a 6. Now, I'm going to tell you a little something about human nature. If I ask you to pick numbers between 1 and 6, you tend to go towards the middle because you're humans. Humans like the middle. All right now. So I betcha a lot of you guys pick 2, 3, 4, or 5. Raise your hand if you pick 2, 3, 4, or 5. That's almost everybody. So isn't it interesting? And I'm just going to go the other way. Did anybody pick 1? One person. All right. So my point is that only one person picked 1 and nobody picked 6. Isn't that interesting? All right. So my point is that humans tend to pick things that are in the middle. I'll give you more proof of that. Do you get that one of the most mean things you can say about somebody politically is that they are extreme? That means they're way on one end. Humans like to think, oh, I'm in the middle. I'm kind of reasonable. I'm normal. And middle, get the whole thing with normal. Here's another one. If a good salesman brings you out to the car lot, they're going to show you 3 cars. They're going to show you a really cheap car that they don't expect you to buy because it's really cheap and it's not that nice. And then they're going to show you this really expensive car. And then you're going to go, well, that's it's nice, but it's super expensive. I can't spend that much. And then they're going to bring you to the one in the middle. And then it'll be like, way better than that cheap car, but not crazy like that super expensive car. And then people choose, well, that seems reasonable. I'll take the middle one. If you're going to offer people 3 options and you want them to take a certain one, put it in the middle. I'm telling you, this is a fact of human nature. All right, so back to... we had a probability of, well, 1 and 2 on the first one, but look at what we have to do for this part. 1, 2, 3, 4, 5, 6. And then 1, 2, 3, 4, 5, 6. Please do that. It's not that hard, making 6 lines. Okay, commenter point? Go ahead.
So, it's a kind of fun comment about probability.
Yes.
So ask someone to choose a random number between 1 and 10.
Yep.
Most people are going to say 7.
It is true. And if I say, think of a flower. Think of a flower. Okay. A large number of you are thinking of a rose. And I'm not saying that all of you are. I'm just saying that a large number of people. And the most common number for people to pick, 7. You're correct. I think people have this feeling about 7s that they're kind of lucky or special. And there are 7 days of the week. There's 7
They're
C's.
not right after 5, but not too close to 10.
Not too high.
It's not
Not too high,
Too predictable
not
because
too
it's
low.
in the middle. 10 and 9 are too high. 1 and 2 are too low.
8 is.
Even numbers feel weird. Odd numbers feel more odd. Odd numbers feel more random.
Yeah.
Interesting. And
That is exactly.
odd numbers are kind of like considered a nicer decoration if you have 5 of something than 4, for example. It's like a better set. If you have 5 flowers instead of 4 flowers, way better. It's interesting. You're right. Lots of human nature there. But this is a tree diagram. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And it doesn't take that long to make, but they're a bit of a pain. But they can answer every complicated probability question. So they're good. Now this one, I'm going to put 0.16 because that's approximately what 1/6 is. 0.16, 0.16, 0.16, 0.16, 0.16, 0.16. And then I should do it on all the rest of them, but I'm getting too lazy. So then to finish my tree diagram, you would have to, and again, I'm not going to make you do this on this one, but I'm just going to show you. This spot right here is heads and a 1. This spot right here, I'm going to sum up. It came up this road here, and it was heads, and then it came out here, and so that's heads and a 2. And then I should say the probability of it after it. This one was heads 3. And the probability of all of them is going to be the same. And I don't know what it is, honestly. I'm going to grab my calculator. I'm going to multiply 0.5 times 0.16. Because that's what you do. You multiply the branches. 0.5 times 0.16 is 0.08. So, this is kind of a boring. There was a 0.08 chance I was going to get any of these combos. They're all the same. So it was equally likely that I could have gotten any of them. All right, I'm not going to keep writing this, but I think you get the idea. This was heads 4, and its probability was 0.08. All right, so let's go on next page. This is the same exact thing except with 2 coin flips. So, draw this. And that green dotted line can be like, that's the end of event 1. We flipped the coin and we either got heads or we got, sorry, not heads or heads, heads or tails. And then you put the probabilities on the branch. Now if we do another coin flip, it's again heads and tails. Heads and tails. And all 0.5s. Sum this one up, it's heads, heads. And its probability, 0.5 times 0.5, 0.25. Heads, tails, probability, 0.25. Tails, heads, 0.25. And the last one was tails, tails, 0.25. Put them all together, you get 1.0. And this is important. Let's start talking about that. All of the events together have to add up to 100%. Now, they might sometimes be off a tiny bit because of rounding. It's rare, but sometimes when you round on really complicated ones, you end up adding them all up and they're off just like 0.01 or something really tiny. Okay. So what is the probability that you're either going to get both heads or both tails? I want to get you used to certain words. Or associate that with add in your head. Just a P, that stands for probability. So if I say P, HH, or TT. Then I just asked you, what's the probability of getting either heads, heads, or tails, tails? And or means add. So there's a 0.25 for this, plus 0.25 for that. What do you think the answer is? 50%, 0.5. Or means add. You know also a keyword, choices. If I say you have this many choices for this and this many choices for that, you're going to multiply choices. If you can remember that to tomorrow, that's going to be the answer to one of our questions. When you have choices, you always multiply them. Like, I'll give you an example. This morning, you had a choice of what clothes to put on. Unless you literally only had one clean shirt, then you only had one choice. But you probably had a couple shirts you could have picked from and a couple pairs of pants you could have picked from. If you want to figure out how many total outfits you could have put on, you say, well, I had 2 shirts and 3 pairs of pants I could pick from. 2 times 3, you had 6 combos you could have done. 6 choices total. You multiply choices, and or means add. All right, moving on to this one. Probability of a path. All right. N1, N2, and N3 represent events along a path. So all this is this saying that you're going to multiply your paths together. Characteristics of tree diagrams. The total number of paths through a tree is the total number of possible outcomes. Oh, so you remember when we had this do, and then we had heads, 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 tails, tails, heads, and tails, tails. Those are all of the outcomes that could happen, and that adds up to 1. All those probabilities add up to 1. We mentioned that already. The vertical sections containing set of branches with the same number of branches in each set. So the point here is that if I make 2 branches here, I gotta make 2 branches there. That one seems kind of obvious to me. If more than one path represents the outcomes, then add those paths. That's like this or this. Or means add. So if there was 2 paths that would win, like as long as you got different outcomes, you win. Well, this is a different outcome. Tails, heads. And this is a different outcome. Tails, heads. Then those are different, 2 different paths, and you do this or that means you would add them together. All right. So here is one that all of a sudden got more complicated because it wasn't the same. Look, it was a 0.42 chance there and a 0.32 chance there. But we know some facts. Like, don't we know that these together have to make up one event?
100.
Yeah, what's D got to be then?
4.
0.4. 0.4. Okay, that makes sense to me. And then use logic. How did this 0.42 happen? Because A had to be what? I'll give you a hint. This times this made that.
7.
Close. 7 probability does not exist. 0.7. 0.6 times 0.7 makes 0.42. And now that I know that's 0.7, I know what B is. 0.3, because together those have to make 100%. That's got to be 0.3. Then I can figure out what C is. And then I know that E and F have to be exactly the same as A and B. No, wait. They must have done something. That feels wrong to me. 4 times 0.7 doesn't equal 0.32. So E should be 0.7. I think they messed up their problem. E must be 0.8, yeah. But that's messed up. I don't know if anybody's caught that before. These events should be the same. The 0.7 and the 0.3 should be repeated down here, and they messed that up. These should be the same as each other.
Put the 7 in. That comes out to 28 words.
If you put the 7 where?
And where the 0.8 is right now, you get the 28 point whatever, 28.
If I put 0.7 here though, 0.7 times 4 is 0.28, not 0.32.
I know, I'm saying like.
Oh, okay,
If we add
yeah.
them all together, it's 100.
Okay, but this can't be, yep, something is messed up in this. So at least I think you understood that these added up to 100% and that this times this had to be that. That's the main point from this slide, so. Sorry about the mistake in the notes. Okay, this one is gonna be really intense. I'm gonna just ask you to draw the lines with me. We're not gonna label every line, it gets too complicated. She teaches 3 classes. Look, first choice, second choice, third choice. Each class has 20 students. Her first class has 12 sophomores. Second class has 8 sophomores. Third class has 10 sophomores. If he randomly chooses a person from each class, what's the probability he will select 3 sophomores? Just to clarify, they never said this. But there could be freshmen, sophomores, juniors, or seniors in the class. And so when they said that the class had 20 students in each class and that there was 12 sophomores, your only choice is it a sophomore or is it not a sophomore? You know, like we're not going to make, they never told us for sure whether they have freshmen or juniors or seniors, or maybe it's only sophomores and juniors. All we know for sure is that they're sophomores and people that are not sophomores. Tate, if there's 20 students and 12 of them are sophomores, what can you tell me?
So,
2 things you could tell me about that. You could tell me the probability of a sophomore. Can you tell me the probability of a sophomore?
6.
Did you take 12 divided by 20?
Yeah.
Excellent. That is correct. 0.6. And then we can just use logic to go, the other one must be 0.4. Or you could say that there's 8 sophomores out of 20. Yes?
So wait, is this just for the first class?
This is our first choice in the first class.
Okay, so are the second choice and third choice the different classes?
I know this, it's kind of a confusing setup, but so far would you agree that let's read the question again. If he randomly chooses 1 student from each class, do you get we're going to have to make a choice in the first class? And that choice is between sophomores or not. So I'm doing the tree right. Whether or not this, I'm just going to scribble those out. I think that they're just going to confuse you. I would have, if I was going to label it anything, I would have labeled it first hour, second hour, and third hour. Okay. My next class, I'm going to pick again. And if I got a sophomore the first time, that doesn't affect this. There's still going to be 2 choices. I'll either get a sophomore or I'll not get a sophomore. And my probability, this is important. Again, something they never said. They never said whether or not I'm going to put that person back into the class. Oh, wait, I'm wrong. It tells us in second hour he's got 8 sophomores. Okay, you can't be in first hour and second hour is something they never said, but we would assume you can't be in 2 of his classes. Okay, so it would be a different set of kids. So this one has 8 sophomores. I'm just going to put 8 out of 20 for my probability. Can you do that? Yes. And then this other one must be 12 out of 20. And that could be made into decimals. That's true. Last but not least, again, a sophomore and a not a sophomore. And in his third class, he has 10. So 10 out of 20. And this must be 10 out of 20 then.
Can you just write half?
Yes, totally. 0.5 is fine. So now I'm going to go and change those. I'm going to use my calculator. 8 divided by 20 is 0.4. So this must be 0.4. And this must be 0.6 then. And 10 out of 20, I like your idea. Let's just make it 0.5 right away. And then, again, like I said, I'm not going to make you finish this whole chart, but I would then need sophomore and not for all these spots. And now, at the end of each branch, you sum up what it is. If, in my opinion, this is the most important part of the chart. This was sophomore, 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 and it comes out to 0.6 times 0.5 times 0.5. I got that from the 3 branches. 0.6 times 0.5 times 0.5, and I get 0.15. There's only a fifth.
There's 1.4.
Oh, sorry, you're right, there's a 0.4 in there. Sorry about that. I'll try again. 0.6 times 0.4 times 0.5. Sorry about that. 0.12. There we go. 12% chance of that. This one is sophomore, sophomore, not sophomore. And that is 0.6 times 0.4 times 0.5. Again, well, I'm smart enough to know I don't have to do it again to get the same answer because it's the same numbers. Now, I'm not going to make you finish it, but if I did, all of these would add up to 100% unless they're off by a tiny bit because of rounding. Okay, now, this is important. Do you get I could get 2 sophomores in more than one way? Let me show you what I mean. I could get a sophomore by starting off by getting a sophomore, and then getting a sophomore here, and then not getting a sophomore. And that's this one. That's one of the ways you could get 2 sophomores. But another way you could get 2 sophomores would be to go, I got 1 sophomore, and then I did not get a sophomore, and then I did get a sophomore. That's another path to the same thing. And you would add up all the different ways that you could get 2 sophomores. You could also not get a sophomore and then get 2 in a row. Sophomore, sophomore. There'd be 1 here. And then you add them all up. Okay. I'm going to go on because I know we have a lot more. There's 13 slides. So, independent versus dependent. This is an important one. Independent things don't affect each other. Like, if I roll this die, and I roll this die over here, does the outcome of that one affect this one at all? Then they're independent. That one came up a 3, this one came up a 6. Doesn't affect it at all. But if instead I take these 4 dice that I have, would you agree there's 2 red ones and a blue one and a white one? See how I got that? There's 4 dice here, 2 reds, a white and a blue. If I just like shake them up so you don't know what's going to come out, and then I drop one out, do you get, there's 2 red ones in here out of 4 dice. There's a 50-50 chance that it's going to be a red one, right? I drop one out, it was a red one. Now, does that affect the probability of getting another red one? Yes, because there's 1 less in there. That's called dependent. So it depends what dropped out. If a red one dropped out, then my probability is 1 out of 3 left. But if something else had dropped out, I might have a 2 in 3 chance of getting a red one then. So, the moral of the story is sometimes things depend on each other and sometimes they don't. Does the fact that it's snowing right now, just a little bit, and it's going to be snowing a lot soon, does that probability affect the probability you're going to get bit by a dog on the way home? Nope, those are called what then? Independent. Okay. Does the fact that your brother is in a really bad mood when you go home and the probability he hits you, do those affect each other? Oh, yeah, because if he's in a really bad mood, it's more likely he's going to smack you on the shoulder because you're being an idiot or whatever. So my point is that things are sometimes independent and things are sometimes dependent. And you got to know how to do them differently in math. So here's the classic marble question. If there was a probability lesson that didn't have marbles in it, I'd be kind of sad. 11 marbles, 5 red and 6 white. I will make you 5 red and 6 white, which I'm going to have to make empty yellow ones. We're going to call those white because I can't draw a white marble without it disappearing on my background. Guess I could have used a black background, but okay. Now, what's the probability of, see that P? Notice how I read it, probability of? Probability of white and then a red with no replacement. Well, first you figure out the probability of the white. What was that? 6 out of 11, good. And then you figure out the probability of the red one, but remember, we have to assume that we got a white one. You know what I mean? We have to know that there is less white ones in there now because we got a white one. Do you get out it's 5 out of 10 then? Does that make sense? There's less white ones now. There's only 5 white ones that you could get because you already got one. Oh, wait a minute. I'm wrong. I am wrong. It is out of 10, but it's not out of 5. My bad. Crap. It actually is, and it's a bad question because it is. Okay. My bad. I should have been saying red ones. How many red ones are there now that I got a white one? There's still 5 red ones. And the answer, the reason I don't like the question is because this is the same exact answer as the probability of a white one and then a white one. Okay, so I'm going to do one last one. Without showing you, tell me the 2 fractions that we would multiply to get this answer. Probability of red one, then red one. This will see if you really know this. Now, some kids asked about their tests. I did get your tests in the grade book, but I did not have a chance to look through and see whether or not you did better on this section than you did on that section. And so your scores are in there, but not the retake part. I will get that done. If you did better on the section and you did your corrections, then you'll get those points. And I don't ever penalize somebody and say, ha, you did worse, so I'm lowering your old test score. I won't do that. But I haven't got those changes in there yet. So I know some of you did better and you want your grade to be raised. I'll get it done. Just give me some time. It's been kind of intense lately. All right, what's the probability of a red one? Well, it's a fraction, and it's out of 11 because there's 11 marbles in the first place. And the probability of a red one is what you want, which is the red ones, out of the possible, which is 11. There we go, 5 out of 11. Now, what's the probability of a red one again? 4 out of 10, there you go. And you multiply your choices. 20 over 110. Could I simplify that? Yeah, that's like 2/11. Could I go decimal? Totally. You could divide 2 divided by 11 and get that if you want. Any questions? Okay, here is a gigantic deck of cards. This is every card in the deck. That's 52 cards. Some of you guys know cards and some of you don't. That's why if we're going to do anything with the card deck, it is a classic example for probability. So we might do stuff with cards, but then we have to give you this up on the board. Okay, I want to know what's the probability of getting a red card and another red card with no replacement. Like I take it out of the deck and I don't put it back. Well, hint, keep your life simple. Aren't half of them red? So the first answer is 5 out of 10, or 1/2, or 26 out of 52. Any of those are equal to a half. But the second one is way more complicated. But if you write it as 26 out of 52, it's not that bad. Then you can just say, well, there's a less chance now I'm going to get a red one. 25 out of 51. There you go. Okay. Now, what if we replaced it? What if we looked at our card and went, okay, I got it. I got a red one, yay, and I put it back. Then it would still be 26 out of 52 again. If I put it back, do you get how this would have stayed exactly the same? If you replace it or not replace it. That is about independent and dependent. If they're exactly the same, that means you put it back, and that means it doesn't matter what you picked first. They're independent. If you change it to like the kind where you don't replace it, and you get 25 out of 51, that meant it depended what you got, and those were dependent. Okay. If you pick 2 cards, what's the probability you pick a club, then a heart? And notice you're replacing. So you pick it, you look at it, you put it back in the deck. Well, there's my 2 picks. You multiply your choices. The first thing is a club. I know some of you aren't good at cards, so I'll tell you, there's 13 clubs in the deck. It's out of 52 possible. Could you have reduced that to 1/4? Yeah. Then a heart. There's 13 hearts in the deck out of 52. That also is 1/4. But why didn't you change the numbers? Because we replaced, as soon as we picked our card, we stuck it back in and the deck was perfect again. And there was still 13 of the kind we wanted and 52 total. If that had been without replacement, it would have been different. I want you to now figure out, same exact question, but if I change it to, they didn't replace the card. They kept the original card out. Then just this one changes to a 51. Raise your hand if you knew that. Okay. Why didn't this one change? Because there's the same number of hearts. We already got a club. The first one was a club. We took a club out. So the hearts is still 13 in there. All right. Good enough on that. We're done with the card examples. And now we have the homework, which is drawing trees. These can be tedious, but I'm telling you, you have a really complicated probability question. Very likely you could draw a tree and answer it for almost every question on the test. Not every question, but tons of your questions. So you got to get good at this, is what I'm saying. This is going to answer tons of the questions on your test, is making trees like this. All right, so let's do it together. Numero uno. I will have you skip some, but to start with, number 1. Carter, you got it up?
What?
Got the worksheet up yet?
Not yet.
Okay, I'll come back to you for number 2. Anders, you got number 1?
Yeah.
Fire when ready. These can be long, I know.
Choose 2 cards, one have its sign from the deck of 52 playing cards. Remember that a normal deck is full suits, so there are 15 clubs, spades, hearts, and diamonds. Do not replace the first card. Round each probability to 3 decimal places.
All right, I got this much. 2, we're going to pick 2 cards. It's out of a 52 card deck, and we're not replacing them.
And then round each probability to 3
All right, so tell me the first actual, like, what do they want? Number one.
Independent or dependent events.
Are they independent or dependent? Good question. We're not replacing the card. So then, does what you got on the second probability depend on what you got on the first? Yes, so it's dependent. Okay, what's question 2? Or is there a part B of number 1?
Draw a true diagram of the situation.
All right. Now, I am not going to make you draw 52 different things. That's crazy. So then what do you do to make your tree? It's either you got what you wanted or you didn't. So for number 2, I'm not quite clear on, is there something I'm missing? Yes.
Yeah, so I wouldn't recommend doing yes or no for this one.
Okay.
Split it into 4 suits,
Ah,
which are 1/4 of each, because the later question is calculate the probability that at least one is a heart, which you're going to need the suits for most likely.
ah,
It's 4 branches.
I like it. Thank you. Clubs, spades, hearts, and diamonds are the 4 suits. If you want to do CSHD, I would totally understand that. And then, it is out of 52, but there is a 1 in 4 chance of each of these. Couldn't you just put 0.25? Am I doing it right? I think I'm doing it right. Somebody was whispering and made me think I was doing it wrong, but I'm pretty sure I'm doing it right. Clubs, spades, hearts, diamonds, 4 choices. And then that's just one event. Now I got to do the other event. Clubs, spades, hearts, diamonds. Holy crap. Then we're just going to figure out whatever part we need to. Because to actually label all of these would take a long time. And now, I think you said that on the next problem, they were going to ask me to do something about, like, probability of hearts.
The first one is probability that you get 2 hearts.
2 hearts. Okay. That would be heart and then another heart. And I'm going to go 0.25 times the 0.25 that would be here. That's 1/4 times 1/4 is 1/16. I can just put in my calculator, 0.25 times 0.25, and I get 0.0. Oh, what? Oh, we remove a card. Thank you. So this isn't 0.25 chance anymore because we already got a heart. So you're right. So this is less hearts, specifically 12 hearts out of, and there's less cards too, 51. So I'm going to go 0.25 times 12 over 51. I'm going to put my fraction parentheses. See, let me just show you. I was typing it in, and I'm smart enough to know this, but did you know this? If I right there put 12 divided by 56, it would screw up the order of operations. Always put your fractions in parentheses. It prevents that from happening. Yeah, it's not 56, that's for sure. Yeah, it's 51. I just couldn't read that, and I had a smudge that I hadn't erased. There. Okay, so 0.25 times parentheses 12 divided by 51. Enter. I got 0.0588, and I think they want 3 decimal places. Did it say?
Yeah.
3 decimals? Okay. 0.059 then. That's intense. This would be a good one to work on with a partner. So, for just a few minutes, I'm going to have these 2 rows. Slide next to each other. I want you to be 6 inches apart and working together. Slide 6 inches apart.
Oh my gosh.
Okay? Slide next to each other.
There's not 6 inches that way.
It's like that.
Not that close. That's not that close.
Right there.
Now you're locked in. Now you
That.
can't go anywhere.
Alright, no.
It's close. A little bit closer. Are you scared?
Bro, you just.
Are you scared?
So you're gonna do
Easier to work together. Closer.
Well, I have. Oh wait, I know what it is.
All right, now I should tell you which ones you can skip. I'll pause when do that. We're skipping problem 4 and 6. So cross off 4 and all of its parts and 6 and all of its parts. So do 1, 2, 3. Skip 4 and 6. And also there's 5 and 7 in there. So skip problems 4 and 6, and that's all I got for you for today.